Dr. Sage here. Today we're going to begin covering Chapter 2. Chapter 2 is an entire chapter on chemistry. I'm going to divide it into two lectures. The first lecture, the one you watch right now, is where we're going to learn about atoms and the periodic table. The second lecture, that's where we're going to learn about chemical bonds. So you're taking a biology course right now, not a chemistry course. So why do we spend an entire chapter learning about chemistry? Well, the reason is because living things, which is what we study in biology, are made up of chemicals. Everything is a chemical. Water is a chemical. DNA is a chemical. Okay, the structures your cells are made out of, what are called macromolecules, we'll learn about them later. Those are all chemicals, things like DNA or proteins or lipids or carbohydrates. So in order to understand biology, you have to understand a little bit about chemistry. Now, with chemistry, a lot of you are coming from different places. Some of you might have already taken chemistry in college. Some of you might be taking it right now the same semester as you're taking biology. Some of you might have taken chemistry in high school. Some of you might have never had an actual chemistry course, and the closest you came was physical science back in like 8th grade. There was like half basic physics and half basic chemistry. So since we're starting from different places, what's going to happen is I'm going to start at a very, very basic level, and then I'm going to build up. So you've already had some chemistry. The very basic level stuff will be a refresher for you, okay? But it's not bad to have a refresher. Okay, and then we'll build up to more complicated topics as we go throughout this lecture and the next lecture. So in that regard, start from the very basics. Organisms are composed of matter. Okay, so what is matter? Matter is anything that takes up space and has mass or has a weight to it. Okay, now even though I just started this lecture, I have to pause the lecture for a second. In this course, as we go throughout this semester, I am going to lie to you. And I need you to be okay with me lying to you. You might have already realized this, or maybe you haven't realized it yet. As you've been going up through your education, you might have realized that some of your teachers have been telling you little white lies along the way. Okay, why is that? Because it's impossible to learn everything all at once. Since you can't possibly learn everything all at once, what we have to do is tell you little white lies to make it easier to understand during the learning process. For example, way back when you were first learning how to subtract, they taught you how to take 5 and subtract 3. Okay, but they told you couldn't, or at least didn't teach you how to take 3 and subtract 5. At the very beginning, they didn't teach you about negative numbers. Why? Because you have to learn things a little bit at a time. So they told you a little bit of a white lie. Now, as you've gone through education, you might, as you kept going up in higher levels of education, you might have thought, you know what, my teacher back then, they didn't know what they were talking about. They told me something that wasn't completely accurate. Now, that is possible, but more likely, they did know what they were talking about. They just needed to tell you a little white lie to make it easier to comprehend. Okay, so you need to be okay with me lying to you. So as long as you're okay with me lying to you, we'll continue. I'll oftentimes point out this is a white lie, so you know that if you keep going up in higher level science, you'll learn the more complete truth. Okay. Now the reason I needed to point that out right now is because I actually just told you a white lie. Because I use the words mass and weight interchangeably, like they're the exact same thing. Technically, they are not the exact same thing. But I don't have time to cover those details. So if you want to learn like what's the difference between mass and weight, take a physics course and they'll tell you the actual difference. In this course, we're going to pretend mass and weight are the same thing. We're going to use those words interchangeably. So that's a little bit of a white lie. Okay, so to continue, matter is made up of elements. Now an element is any substance that cannot be broken down into other substances by chemical reactions. Now that definition is a little bit confusing. So what is an element? Elements are things you've heard of before. For example, let's say you have a piece of pure aluminum, okay, and all that is made up of aluminum. There's nothing else there. Well, that's made up of the element aluminum. Or you have a container of oxygen, and there's nothing in that container except for oxygen. Well, inside that container, that's made up of the elements of oxygen. So elements are things you've heard of before, like carbon and hydrogen and oxygen and nitrogen and helium. Those are all elements, okay? Now, a compound is a substance consisting of 2 or more elements in a fixed ratio. So, for example, a compound that I can guarantee you've all heard of before, and I can almost guarantee everyone actually knows the chemical formula for the compound, is water. Okay, everyone knows that water is H2O. Okay, now what that means is one molecule of water has one oxygen atom and two hydrogen atoms. So therefore it's a compound. It has more than one type of element. It has oxygen and hydrogen, and it's in a fixed ratio. Water is always H2O. Water is never H2O2. That would be hydrogen peroxide, which is a different substance from water. Okay, so that's an example of a compound. Now, another thing to note about compounds is that they can have characteristics different from the elements that make it up. Let me give an example of that. Here is an element, sodium. Okay, sodium, if you have pure sodium, it's a solid, okay? And this solid reacts very strongly with other elements. In other words, it can react explosively with other elements. And here's another element, chlorine. Chlorine is not a solid, chlorine is a gas. It's the gas inside this container. Now, chlorine gas is poisonous. If you breathe it in, it can kill you. Now, if you take these two different elements and you combine them together, if you take this explosive solid and this poisonous gas and put them together, what they create is sodium chloride, or table salt, which is safe to eat. So obviously, this does not behave the same as the elements that make it up. Okay, so that's an example of a compound. Now, since we're studying biology, what we care about in this course the most is the elements that are required for life. Out of all of the elements, if you are alive, and it doesn't matter if you're a human, a mouse, a worm, a fly, a yeast, a bacteria, a plant, if you're living on this planet, about 96% of you is just made up of 4 elements. Those 4 elements are carbon, hydrogen, oxygen, and nitrogen. Okay, so that's what makes up the vast majority of all living things, just those 4 elements. Now, most of the other 4% is made up of calcium, phosphorus, potassium, and sulfur. And then there are elements that you do also need to live, but in very, very tiny amounts. Those are then called trace elements because you need them in such small quantities. For example, you can't live without iron. Okay, you need iron in order to live, but you only need it in very, very, very tiny amounts, so that's called a trace element. Now, in this course, obviously, since it's studying biology, we're going to focus mostly on these 4 in this course. If you want to learn all the details about all of the other elements, take chemistry, and they'll teach you details about those elements. So, there are different elements, like carbon is different from oxygen. Oxygen is different from hydrogen. Okay, why are they different? Because each element consists of unique atoms. Okay, well then what is an atom? An atom is the smallest unit of matter that still retains the properties of an element. In other words, if you have a single atom of carbon, it behaves like carbon. If you have a single atom of oxygen, it behaves like oxygen. Now, atoms can be broken down into smaller pieces. But once you break them down into smaller pieces, they no longer behave like the element they were. So atoms are made up of smaller pieces. Those smaller pieces are called subatomic particles. There are 3, white lie, subatomic particles, okay, neutrons, protons, and electrons. Technically, you can break these down into smaller pieces, but if you want to learn about that, you got to take a physics or maybe a chemistry course. Okay, so for this course, white lie, atoms are made up of 3 subatomic particles. Those subatomic particles, the protons, have a positive electrical charge. Okay, so with electricity, there are 2 different charges. There are positive electrical charges and there are negative electrical charges. Okay, well, the protons have a positive electrical charge, a +1 electrical charge. Okay, now that one should be fairly easy to remember. Why? Because protons are positive. Okay, so that's protons. Another subatomic particle is a neutron. Neutrons do not have an electrical charge. They don't have a positive or a negative electrical charge. So again, that one's kind of easy to remember. So neutrons are neutral. They don't have an electrical charge. The last one would be the electrons. Okay, so it would have what remains left as far as charges. If you already have positive charges And neutral, what you have left is negative charges. So electrons have a negative electrical charge or a -1 electrical charge. Neutrons and protons and electrons are subatomic particles. So they're made up of matter. Remember, matter is anything that takes up space and has mass or has a weight to it. So these things do have a mass or a weight to them, but they're very, very small. Okay, so since they're so small, you can't weigh them in the way you're used to think about measuring weight. So in the United States, you're usually used to think about measuring weight in like pounds. In science, we don't typically use pounds. What we use is most of the time is like grams, okay, or kilograms. But atoms are very small, so we can't measure them in the usual units of mass like grams. They're too small for that. So we need a different unit of mass. Okay, just like similarly for like length. You can measure length with different units of measurement. Like you can measure length in inches or feet or miles or meters or kilometers. It's all just different ways of measuring length. Well, mass you can measure with pounds or grams, or for things that are very, very small, the unit of measurement is called a Dalton. Now, a Dalton is also called an AMU, or atomic mass unit. Unfortunately, this happens way too much in science, but a lot of times in science there'll be more than one name that means the same thing, and you got to know both names. So a Dalton is the exact same thing as an AMU, or an atomic mass unit. It's a unit of measurement of mass for things that are very, very small. Neutrons, they have a mass. One neutron weighs exactly 1 Dalton. Okay, so that's easy. Protons, they have a mass. One proton weighs exactly 1 Dalton. Okay, so neutrons and protons weigh the same amount. They each weigh 1 Dalton or 1 AMU. Now, electrons do have a mass. However, because their mass is so much smaller than the neutron or the proton, we ignore their mass. It takes almost 2,000 electrons to weigh as much as 1 proton. So since its mass is so much smaller, we just ignore its mass. We pretend it doesn't have a mass. In reality, it does have a mass. We just kind of ignore it. So, in atoms, the neutrons and the protons are at the very center of the atom, which is called the atomic nucleus. That's where you find all the protons and all of the neutrons. That's not where you find the electrons. The electrons are outside of the nucleus in an area called the electron cloud. Okay, or this is a model of an atom. Okay, so in the center of the atom, you have the nucleus. That's where you find all of the protons and all of the neutrons. Outside of this nucleus, this area out here, that's called the electron cloud. Okay, and that's where you find all of the electrons. Each proton has a charge of +1 electrical charge and weighs 1 Dalton, or 1 AMU. Each neutron is neutral, it doesn't have an electrical charge, and it weighs 1 Dalton, or 1 AMU. Each electron has a -1 negative electrical charge, and we ignore its mass because it takes almost 2,000 of these to weigh as much as 1 of these. So we just ignore its mass. So that's a model of an atom. But honestly, it's a pretty crappy model of an atom. It's not a very good model of an atom. So for just a minute, what we're going to do is we're going to build a model of an atom inside our heads. So inside your heads, picture a marble. You've all seen a marble before, at least on a TV show or something. You've seen a marble. That marble is going to represent the nucleus. So that's where you find all the protons and all the neutrons. Now you take that marble, that's the nucleus, and you put it in the center of a baseball stadium. The entire rest of the baseball stadium, that's the electron cloud. That's the place where you find the electrons. Now, of note, the baseball stadium is not filled up with electrons. The electrons are 2,000 times smaller than that marble. That electron cloud is simply the space the electrons are traveling through. Okay, so that's the real scale of an atom. Like the nucleus is marble compared to the baseball stadium, that's the electron cloud, and the electrons are 2,000 times smaller than the marble, just traveling around the baseball stadium. That's the real scale, but you can't possibly draw that scale, so we use models like this to represent it. Okay, so now what we're going to do is we're going to go through each type of subatomic particle, and we're going to learn why they're important. The first one we're going to start with is the proton. Okay, it turns out that the reason the proton is important is because it determines which element it is. For example, carbon, that's one of the elements. Carbon always has exactly 6 protons. Why? Because that's what makes it carbon. Every single carbon atom has exactly 6 protons. If you find an atom out there in nature and it has exactly 6 protons, that is carbon. That's what makes it carbon. In contrast, oxygen has exactly 8 protons. Every single oxygen atom has exactly 8 protons. Why? Because that's what makes it oxygen. Hydrogen has 1 proton. Why? Because that's what makes it hydrogen, the fact that it has 1 proton. So the protons are very important because they determine which element it is. Now, because that's very important to know, like which element you're talking about, we give the number of protons a special name. We call the number of protons its atomic number. So the atomic number is the number of protons that an element has, and that determines which element it is. Like carbon has 6, oxygen has 8, hydrogen has 1. Okay, so that's why protons are important. Now, next subatomic particle, neutrons. Why are neutrons important? Well, first, so atoms have an atomic number. That's the number of protons it has. It also has a mass. So an element's mass number is the sum of protons plus neutrons added together in the nucleus. The atomic mass is the atom's total mass, and it can be approximated by the mass number. Okay, this is another one of those little white lies. In this course, we're going to use mass number and atomic mass interchangeably, like they're the exact same thing. Technically, they're not the exact same thing. We don't have time to go into those details. Take chemistry if you want to learn the differences between them. Okay, so for us, mass is how much an atom weighs, and it's also the number of protons plus neutrons added together. Why do we care about neutrons? Well, it turns out that atoms can have different numbers of neutrons. All atoms of an element have the exact same number of protons. Remember, that never changes. That's what makes it the element it is. Every single carbon atom has exactly 6 protons. That's what makes it carbon. But there are different types of carbon. Okay, you can have a carbon that has 6 protons because it always has 6 protons and has 6 neutrons. Or you can have a carbon that has 6 protons because it always has 6 protons and has 7 neutrons. Or a carbon that has 6 protons because it always has 6 protons and has 8 neutrons. These are all carbon because they all have 6 protons, but they have different numbers of neutrons. So there's a name for that. Those are called isotopes. Isotopes are the same element but with different numbers of neutrons. Now, for the most part, the isotopes, usually they behave the same, like in chemical reactions, which we'll learn about later in the second video in this series. In chemical reactions, this carbon and this carbon mostly behave the same. The main difference between them is they weigh different amounts. This one will weigh 2 daltons more than this one because it has 2 neutrons more than that one. But sometimes you do need to be able to differentiate them. Like, are you talking about this carbon or this carbon? In that case, what we do is we refer to them by their mass. Like this one we would call carbon 12 because it weighs 12, 6 protons plus 6 neutrons. This one we call carbon 13 because it weighs 13, 6 protons plus 7 neutrons. This one we call carbon 14 because it weighs 14 daltons, 6 protons plus 8 neutrons. Okay, so if you have to specify, you just call it by its mass, carbon 12 versus carbon 14. Now, for the most part, isotopes behave similarly in chemical reaction, but there is a special type of isotope. That's called a radioactive isotope. What a radioactive isotope is an atom that's not stable. It's breaking apart over time. It's falling apart. And as it falls apart, it might give off electrons or neutrons or protons. And at the same time, it's also going to be giving off energy. And the form of energy it's going to be giving off is radiation. That's why it's called a radioactive isotope. Now, why do we care about radioactive isotopes in a biology course? We're not taking chemistry, we're taking biology. Well, because we use them in science and in medicine all the time. For example, one way of using radioactive isotopes you might have heard of before is called radiocarbon dating. Like if you dig a fossil out of the earth, how do you know how old that fossil is? Okay, well, one of the atoms, carbon 14, is a radioactive isotope, and it's unstable. It's breaking apart over time. Okay, well, when you dig up that fossil, if you compare how much carbon 14 does it have compared to how much carbon 12 does it have, you can determine how old that fossil is. Why? Because carbon 14 breaks down at a very exact rate. It's like a clock, how fast that carbon 14 will break down. So if you can determine how much carbon 14 is left, then you know how old that fossil is. Now, we also use radioactive isotopes in medicine. For example, there might be a time where you have to go to the hospital and they're going to do a diagnostic test on you. And before they do the test, what they do is they give you this container of sugar water, and they tell you drink this sugar water. Okay, well, why are they telling you to do that? Well, the reason is because, well, we'll learn in much greater detail in a later chapter, your cells need energy for everything they do. Okay, obvious things like moving muscles requires energy. Less obvious things like thinking actually requires a lot of energy. Even less obvious things like building DNA or building proteins requires energy. So you need energy to do all the work that your cells need to do. Where do you get that energy from? You get it from the food you eat. Okay, well, your cell's preferred source of energy is pure sugar, so glucose. So they give you this glucose, this sugar solution, tell you to drink it. Why? Because they want to know where that glucose is going in your body. Because wherever that glucose is going, those are the cells that are using a lot of energy right now. So they're trying to figure out which cells are using a lot of energy. But once you drink that glucose, you can't see it inside your body anymore. However, that wasn't just glucose. That was glucose that was tagged with a radioactive isotope. Okay, why do we do that? Because we have very sensitive equipment that can detect very, very small amounts of radiation. So you drink that small dose of radioactive glucose, and then they do a test on you, for example, a PET scan, to determine where that radioactive isotope is now inside your body. And you can do this to learn things. So for example, give you that radioactive isotope and do a PET scan of your brain, and you can see which areas of the brain are the most active right now based upon where the most of that radiation is. And you can do that to compare with different individuals. So for example, a normal individual is somebody who's suffering from Alzheimer's disease, okay, where it's much more difficult for them to be able to think. Okay, so that's an example of why we use radioactive isotopes in biology, which is a type of isotope, which is the same element, but with different numbers of neutrons. Okay, so that's why neutrons are important. The last subatomic particle we're going to talk about is the electrons. Okay, so why are electrons important? Well, before I can explain that to you, I have to actually teach you a little bit about energy. Okay, so energy is not just like the electricity coming out of your outlet. Okay, there's actually lots of different types of energy. Technically, energy is the capacity to cause change or the ability to do work. And there's lots of different types of energy, like electrical energy is one type of energy. Light energy is another type of energy. Okay, or another category of energy is called potential energy. Potential energy is energy that's stored that can later be used to do work. For example, if I hold this marker up here, it's storing energy. Okay, why? Because it doesn't want to be held up here, it wants to fall towards the earth. Okay, so it's storing energy that could be used for it to fall towards the earth. So that's stored energy, that's potential energy. With this example, that's called gravitational potential energy. Okay, so potential energy is just stored energy that can be later used to do work. So it's energy that matter has because of its location, like the marker being held off the ground, or its structure. Okay, it turns out that chemicals store energy. We'll learn that detail in a later chapter. The other thing to note is that this marker can store different amounts of potential energy. Like if I'm holding it up here, it's storing more energy than if I were holding it down here, because down here has a smaller distance to fall, up here has a bigger distance to fall. So this is storing more energy, this is storing less energy. Okay, so this marker can store different amounts of potential energy. Okay, so why am I teaching about potential energy? Because it turns out that electrons are storing potential energy. And just like the marker, the electrons can store different amounts of potential energy. The amount of energy the electron is storing is called its energy level or its electron shell. Let me explain that a little bit better in a figure. So here's a model of an atom. Okay, so this would be the nucleus. That's where you find all of the protons and all the neutrons. Outside of that, that's where you find the electron cloud. That's where you find the electrons. Now those electrons can actually be in different places. Okay, the electrons can be, let's say, right here, which is very close to the nucleus. That's called the first electron shell. Or they could be farther away, like over here. Farther away from the nucleus, called the second electron shell. Or farther away, let's say over here, that's called the third electron shell. Okay, now it turns out the electrons want to get as close to the nucleus as they can. Just like this marker wants to get as close to the ground as it can, the electrons are going to get as close to the nucleus as it can. Well, the closest that the electrons can get to the nucleus is the first electron shell. And in that case, it's storing the least amount of energy. Just like the closer the marker is to the ground, the less energy it's storing. Okay? The second closest they can get is the second electron shell, so they're storing a little bit more energy. Just like the marker here has less energy, farther from the ground, more energy, farther from the ground, more energy. Or the electrons, closest to the nucleus, least energy, farther from the nucleus, more energy, farther from the nucleus, even more energy. Those are electron shells. Now it turns out the electrons can actually move to different electron shells, just like this marker can move different distances from the ground. And you've actually seen the results of electrons moving, you just didn't realize that's what you were witnessing. Because, especially living in Central Florida, you've all seen a neon sign before. Okay, so what is a neon sign? It's just a glass tube filled with atoms of the element neon. So neon is one of the elements. Okay, then what happens is you pass electricity through those neon atoms. Okay, as we pass electricity through these neon atoms, it gives the neon atoms more energy. And that energy has to go somewhere. Where it goes is it goes to the electrons. And it causes the electrons to go from a lower electron shell to a higher electron shell. Okay, those electrons become what's called excited, so they now have more energy they're storing. But the electrons don't like that. Just like the marker doesn't want to be up here. If we're up to the marker would be down here on the ground. Okay, the electrons don't like being in this higher electron shell. They want to go back down to a lower electron shell, and they actually can move back down to the lower electron shell. But in order to do that, they have to give away that extra energy. And they do give it away in the form of light. So the light that you see in a neon sign is the energy coming from electrons as they're going from a higher electron shell to a lower electron shell. So you've witnessed the results of electrons moving, you just didn't realize that's what you were watching. So why do we care that electrons store energy and that they can store different amounts of energy? Well, because it turns out that the chemical behavior of an atom is mostly determined by the distribution of the electrons in the electron shells. Which electrons they have in the different electron shells determines how that atom is going to behave. Now, what do we mean by behave? What I mean is how it reacts in chemical reactions. So we're very interested in how the atoms are going to be reacting, and therefore we're very interested in how many electrons are in the different electron shells. Now, there's a way of representing all the different elements and actually representing the distribution of the electrons in the electron shells, and that's through something I guarantee you've seen before, which is called the periodic table. So here's an example of the periodic table. Now there is a lot of information in the periodic table. We are definitely not going to cover all of it. If you want to learn all the details about the periodic table, take a chemistry course. But there is some things we do need to understand about the periodic table. First thing is that each box represents a different element. For example, up here we'd find the element hydrogen. Over here, carbon. Over here, oxygen. Okay, so each box is a different element. Now, inside each box is a set of information. For example, let's say I take this element right here, and I'll just rewrite it. It says 6C12, okay? So inside each box of the periodic table, you find a number, okay? That first number at the top, that's called the atomic number, which I taught you what that was. That's the number of protons an element has. Now, it makes sense to list the number of protons because that's what determines which element it is. Remember I said that carbon always has exactly 6 protons? Well, carbon has the number 6 here. Oxygen always has 8. Oxygen has the number 8 there, okay? So that's the atomic number, the number of protons. Then you have some letters. That's the atomic symbol. That's what we use to represent the element. Now, some of those will make obvious logical sense to you. Like it might make sense that H is hydrogen, C is carbon, O is oxygen, Ca is calcium, but some of them might not make logical sense to you. For example, here, this element says Na. Okay, well, Na is sodium. Well, you don't spell sodium with the letters Na. So why is that? Well, because this is not the periodic table of the United States. This is the periodic table. Okay, all scientists use the same symbols to represent the elements, no matter what native language you're speaking. So some of these might not be based upon English words. Some of them may be based upon German or Latin or other languages. So some of them might not be as obvious to you, like Na for sodium. Okay. All right, so we have the atomic number, we have the atomic symbol. Then underneath that, what you have is the mass. Okay, remember the mass is how much one atom weighs in Daltons. So for example, one carbon atom will weigh 12 Daltons. or 12 AMUs. Remember, that's the same thing. That's how much one single carbon atom weighs. Remember, that's also the number of protons plus neutrons added together. So, if I give you this for carbon and I say, well, how many protons does carbon have? That's easy. It has 6. That's its atomic number. I say, okay, well, how many neutrons does it have? Well, this number at the bottom is neutrons plus protons added together. So if you want to know how many neutrons it has, it's 12 minus 6, or has 6 neutrons. Or in the case of sodium, it says 11 Na23. So sodium has 11 protons, 23 minus 11, or 12 neutrons. Okay, so that's protons and neutrons. How about electrons? Well, it turns out for a standard atom, not an ion that we'll learn about in the next video, but for a standard atom, atoms are neutral, which means they need to have the same number of positive protons and negative electrons to cancel each other out. So if carbon has 6 positive protons, it's going to have 6 negative electrons. If sodium has 11 positive protons, it's going to have 11 negative electrons. Okay, so that's the information inside each square. And again, I told you a little bit of a white lie, because if you notice, I said sodium is 23, whereas it actually says 22.99. Okay, again, to learn the differences, take chemistry. For us, we're just going to round the numbers. Okay, so the next thing to know about the periodic table is how it's organized. If you look at it as a very distinct but kind of unusual shape. All right, so how is the periodic table organized? It's actually organized several different ways at the same time. The first way it's organized is based upon increasing atomic number. Now that one makes perfect logical sense, since the atomic number determines which element it is, like hydrogen is 1, carbon is 6, oxygen is 8. It makes sense to organize it based upon that atomic number. How's it organized? The same way you write. Okay, when you write something, you write from left to right and then top to bottom. Okay, well, the periodic table is organized the same way. You start over here with number 1. You go across to number 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So it's written based on increasing atomic number. Ignore this big gap in the middle here. I'll kind of explain that in a minute. But that's the first way it's organized, based on increasing atomic number. The next way it's organized is actually based upon the electrons. Okay, so to explain that, what I'm going to do is I'm going to take just these first 3 rows. We're going to look at just these first 3 rows here. We're going to ignore the whole rest of the periodic table. And we're going to take these 3 rows and we're going to squish them together. Okay, so if we do that, then it would look like this. Now, in this version of the periodic table, I also have a little model of the atom. So up here at box number 1, that's hydrogen. Okay, this is the nucleus of hydrogen, which is where you find the protons, and if they have neutrons, is where you find the neutrons. And then there's a circle outside of that represents the first electron shell. Now, hydrogen has an atomic number of 1, which means it has 1 proton, and therefore it also has 1 electron. So we're going to put that 1 electron, that's this dot here, on that first electron shell. Okay, then the next element has an atomic number of 2, that's helium. So helium with an atomic number of 2 has 2 protons, therefore 2 electrons. So we put the 2 electrons, the 2 dots, in that first electron shell. Okay, so the next element, which has an atomic number of 3, that would be lithium. Okay, there's a bit of a problem. And the problem is that first electron shell can only hold at most 2 electrons, and it's full. It can't fit any more. Okay, but lithium has 3 electrons. So what happens is the electrons, they want to get as close to the nucleus as they can. So the first 2 electrons will go into the first electron shell, and then it's full, it can't fit anymore, but there's 1 more left over. So that third electron then goes into the second electron shell. Okay, so the next element that has 4 protons, 4 electrons, 2 in the first shell, 2 in the second. Then 5 electrons, 2 in the first shell, 3 in the second. Then 6 electrons, 2 in the first shell, 4 in the second. Then 5 in the second shell, 6, 7, 8 electrons in the second shell, and then white lie, the second shell is full. It can't fit any more. Okay, so that was neon, it had 10 electrons. 2 in the first shell, 8 in the second. So the next element, sodium, has 11 electrons. What's going to happen is 2 will go into the first shell, then it's full. 8 will go into the second shell, and then it's full. That leaves 1 left over, which is then going to go into the third electron shell. And then you start filling the third electron shell with 1 electron, 2, 3, 4, 5, 6, 7, and then 8 electrons, a filled electron shell. So what maybe you noticed, maybe you didn't notice, is that every time we add a row, what we're doing is we're adding an electron shell. The first row only uses a first electron shell. The second row uses a first and the second electron shell. The third row uses a first, second, and third electron shell. So the second way the periodic table is organized is based upon the rows. Each row adds an electron shell. Okay, now, I mentioned white lie a minute ago. In this class, what you need to know is the first electron shell can hold at most 2 electrons and then it's full. Every electron shell after that can hold at most 8 electrons and then they are full. It's a little bit of white lie. You can't actually fit more than 8, but if you want to learn about that, take a chemistry course. We're going to pretend that doesn't happen. So for us, first electron shell can hold at most 2 electrons. Second shell, third shell, fourth shell, etc. They all hold at most 8 electrons. Okay. Now, so that's the second way it's organized, is based upon the rows. Third way the periodic table is organized at the same time is based upon columns, up and down. It turns out that everything in a column has something in common. Okay, for example, this first column here, all of these elements have 1 electron in their outermost shell. Okay, all of these have 2 electrons in their outermost shell. You know, this uses the first and the second shell, but the second shell has 2 electrons in it. These use the first, second, and third electron shell, but the third electron shell has 2 electrons in it. Okay, then you have 3 electrons in the outermost shell, 4, 5, 6, 7 electrons in the outermost shell, then a filled outermost shell, which is either 2 out of 2 for this one or 8 out of 8 for the rest of them. Okay, so the third way it's organized is based upon the columns, which is the number of the electrons in the outermost shell. Why bother to organize it like that? Well, because it turns out that the main thing that determines how an atom behaves in chemical reactions is how many electrons it has in its outermost shell. Okay, recall that I told you that sodium is a solid that reacts very strongly with other elements, or reacts explosively with other elements. Why does it do that? Because it has 1 electron in its outermost shell. Okay, that's why it behaves so strongly with other elements. Well, everything in this first column, go back to the big picture, everything in this first column has 1 electron in its outermost shell. What that means is they all are going to behave similar. They're going to react very strongly with other elements. In contrast, carbon will react with other elements, but not as strongly. But everything in this column reacts similarly to the way carbon does. However, on the other hand, if you have a neon atom, it will never react with other atoms. Now, what do I mean by react? What I mean is form chemical bond. For example, go back to water that everybody knows is H2O. What that really means is it's 1 oxygen atom with chemical bonds to 2 hydrogen atoms. What I mean by react is I mean form these chemical bonds here. Okay, you'll never find a hydrogen atom by itself in nature. It'll always be bound to another atom. Why? Because it reacts very strongly with other atoms. In contrast, if you find a helium atom or a neon atom in nature, it will never be attached to another atom. They're always by themselves, okay? Why? Because they already have a filled outermost electron shell. It turns out that the only thing that every atom wants in their life is a filled outermost electron shell. That's the only thing they're looking for, okay? Well, all of these atoms, they already have a filled outermost electron shell. Okay, so they're called chemically inert. They don't react with other atoms. In other words, they already have the only thing they want in their life, a filled outermost electron shell. However, all of these atoms, they don't have what they want. They're unsatisfied with their lives. They don't have a filled outermost electron shell. Okay, so what they're going to do is they're going to get together with other atoms to try to fill their outermost electron shell. And when they do that, they form chemical bonds. We'll learn the details of how that works in the next video in this series. Okay, but what this tells us is that the way an atom behaves is based on the number of electrons in the outermost shell. These ones that have a filled outermost shell, they want to be alone. They're loners, they're happy by themselves. All of these ones, okay, they're codependent. They can't handle being alone. They need to be together with another atom to try to fill their outermost electron shell. Okay, so back to the periodic table. Up here, everything in this column has 1 outermost electron. 2, we're going to pretend these do not exist. Take chemistry to learn about these. we're just going to pretend they don't exist. 3 outermost electrons, 4, 5, 6, 7, and then a filled outermost electron shell, which is 2 out of 2 for this, or 8 out of 8 for the rest of these. Okay. So obviously, the outermost electron shell is very important, so we give it a special name. The electrons in the outermost electron shell are called valence electrons, and the outermost electron shell is called the valence electron shell. The chemical behavior in an atom is mostly determined by the valence electrons. Elements with a filled valence electron shell are chemically inert. They don't react with other atoms. Now, electrons are in the electron cloud. At the same time, they're inside electron shells. At the same time, they're inside orbitals. Okay, so an orbital is a three-dimensional space where you find an electron most of the time. So physically in space, where do you actually find the electrons? And each orbital can hold at most 2 electrons. That's all the details we're going to learn about orbitals for this class. Take chemistry and you'll learn a lot more more than you want to know, frankly. Details about orbitals, like they come in different sizes and different shapes, like these spherical ones here versus these dumbbell-shaped ones here. Take chemistry to learn about that, and they fill in different orders. Take chemistry. For us, an orbital is a physical space where you find an electron 90% of the time, and each orbital holds at most 2 electrons. So now we talked about the subatomic particles, protons, neutrons, and electrons, and why they're important. We talked about atoms, we talked about the periodic table, we talked about elements. In the next video in this series, we're going to learn about how those chemical bonds form and what the chemical bonds are. So until then, this has been Dr. Sage.